and we're on page 298, though it might have just now started. So 298 and 5 steps for a 5. Okay, so as far as a galvanic cell goes, remember that in our galvanic cells, we're talking about them being spontaneous. So if it's spontaneous, it's going to be happening on its own. And so the way that's going to happen is because it's able to produce energy. So my energy made is going to be a positive value. I'm producing energy, and then this is how we make our batteries in our world. So the way we set it up in lab is you end up with 2 beakers. Both beakers have to have a solution in it. They both have to have an electrode, and those electrodes need to be connected in some way. There's typically a device here, and what's different from electrolytic cells is here this is just going to read the voltage that you're creating. It is not going to provide any voltage. So it's not a power supply. This is just be like a voltmeter. And then within the cells, each side, the requirements need to have your electrode needs to be made out of the same material as your solution. So we are looking at aluminum and nickel were some examples they had readily available in the book. So you would have a solution that is filled with the ions of one, and then your metal has to be made of the other. So this would be an aluminum metal, and this would have to have aluminum ions. There's no way to get aluminum ions into solution without there being some solid that you measure out, so it has to have a negative component with it. It can't just be the cation. So we tend to choose those negative components that don't react with anything. So like nitrates are good examples. Sulfate is often used. I'm going to use nitrate here. Chlorides sometimes can be used. You just have to be careful because there's a few things that reacts with. So obviously these are not proportional because you'd have more nitrates in here than you would have of aluminums. Let's find a place to start. And then on the other side, I'm going to use nickel. So once again, my metal needs to be the same. And then I need to have a material. It's nickel 2. And so I'm going to put it with nitrate again because we know that's always a good one to put it with because that's the only anion we know that's always going to be non-reactive. And then the last thing you need is a salt bridge because you have to have a way to complete the circuit. Our electrons are going to be flowing up here. And please remember that. Don't say on the AP test that our electrons are going anywhere else. But our electrons flow across the top one direction or the other. And then in here, this salt bridge is a way for our ions to travel so that we can maintain neutrality of our solutions. And so your salt bridge tends to be made out of a substance that's very non-reactive. So an alkali metal and maybe nitrate, or an alkali metal and chlorides. Same deal. Those are the most common salts that you would see in your salt bridge. And they usually have these little cotton balls at the end to kind of hold it together. So that would be our total setup. And then the next job would be to figure out who's getting oxidized and who's getting reduced. So before I talk about that, do you guys have any questions about the setup? Okay, super. So in the AP test, they're going to give you a few values to kind of compare to. And these up here are standard reduction potentials for those, for the nickel, the aluminum, and hydrogen. I put hydrogen up here because it gives me a good opportunity to remind you what these potentials are. Remember, these were discovered a long time ago. And so what the scientists did was they determined what hydrogen's volts were and made it 0. So it was our standard of comparison. And then everything is just based on that. So these values are slightly arbitrary, but they're the ones that we use. We're on 298. And so that's why we don't change those numbers other than flipping the sign, but we would never multiply or divide these numbers because they're just based on comparisons. Anyway, all right, so our job is to figure out who's going to be gaining electrons and who's going to be losing electrons. Both of these reactions are written in the reduction form. And in the reduction form, you know that because we have the positive electron coming together with the ion. So the positive electron, positive ion coming together with the electron. So they're going to squish together so that ion is gaining the electrons, and you're producing this solid. So this is the reduction version of both. And so between the two, you've got a negative 0.23 volts is what's going to occur if this reaction were to happen, and it's negative 1.66 volts if this reaction were to happen. So the one that's more likely is going to be the one that's more positive or closer to being positive. So far, so good? So we're going to take nickel as the one that's likely to be reduced. Okay. So we're going to call this side reduction. And if it's reduction, does that make it the cathode or the anode? Cathode, because red cat. Or, because red cat. Don't say things like that on the AP test. Cathode, and a good way to remember that is they're both vowels. Cathode is where reduction happens. So the thing that's actually the cathode is the electrode. So that would make this guy the anode. And that's oxidation. These are both the vowels. And you can say anox if you want to talk about animals. So that tells me that this needs to be oxidation that's occurring. And so what I see right now that's happening, we've got it set up for reduction. So in order to figure out what my overall reaction is, I'm going to need to flip that equation around. So I'm going to take my aluminum here, and what's really going to be happening is that aluminum solid will be breaking apart and creating aluminum ions and some electrons. And so that is going to be partnered with the nickel reaction. And since nickel's reaction is happening as is, I'm going to leave it at the 0.23 volts, but the aluminum reaction is happening in the reverse. So I'm going to flip the sign because it's going to actually make energy, which is good because when I find my sum of these, I want it to be a positive value because we said earlier that's what galvanic cells are. Okay, and so I'm going to sum them up. We recognize here, though, there's a problem with our electrons because I've got 3 on the top, but only 2 on the bottom. So I'm going to balance those out, and I'm going to multiply it so that this top I have 2 aluminums, and that gets me 6 electrons. On the bottom, I'll have 3 nickels, 6 electrons, and 3 nickels. Remember, that still doesn't have any impact on my volts over here. It just helps me to understand overall 6 electrons will be transferred, and that's a good question AP might ask you. So you can kind of see how it balances, but that does not impact this value here. So then my overall for my equation, I'm going to get 3, 4. Whoa. Okay, 1.34. 1.43. It's been a long morning, sorry. And so then what I want to do is tell you more information. What else do I need to tell you? You guys have questions? So this number is how much energy we're going to make.
Mr. Crawford, you left a couple of items in the main office. Those items are being delivered to the classroom that you're substituting in today. Thank you.
So you put the fail 3+ because it's oxidation?
Yes. That was the other thing I wanted to say. Okay, Michael, you had a question, and then I want to talk about electron transfer.
So between nickel and aluminum, you said that nickel is more likely to be used because it has a higher reduction.
Right.
So that with saying between which one of the two is stronger reason.
So when you're looking at it being a reducing agent, what you would be looking at is it itself is being oxidized because the reducing agent is causing the other one to be reduced. But that's terminology that's confusing, and they've pulled it off of the AP test. So that terms of reducing agent and oxidizing agent, they've gotten rid of totally. So if they were to ask a question like that, the question would be, which one is more likely to be oxidized? And that would be what they were getting at. Does that make sense? Yeah. Reducing agent and oxidizing agent is sort of silly terminology. So I'm glad, that's one I'm really glad they got rid of. Okay, so I did want to say, one thing they often will ask is drawing which way our electrons are going. And so since the cathode side is gaining the electrons and our anode side is losing the electrons, then we know our electrons are going to be traveling this way through our cell so that this one can be losing it and that one can be gaining it. So then overall, you want to think about which way our ions will be traveling. So if my electrons are leaving here, that means my aluminum metal is going to be breaking apart into aluminum ions. So I'm going to have more Al+3 building up in here. So my positive charges are going to increase within the solution. And since we can't have a imbalance of solution, the negative nitrates will travel from the salt bridge into solution to maintain neutrality. And that's the best way to explain that. And our ions will travel towards the anode side here, where we've got a buildup of our positives to maintain our neutrality. And then on this side, my nickels are going to be decreasing. So I'm going to be losing my positives. And so that means my cations from my salt bridge will be traveling in there, again, to maintain neutrality so that my solutions don't have a buildup of too many positives or too many negatives. And that is definitely a question that was, I think we did that practice one they asked last year, where you had to draw your salt bridge and show the ions in there and show which way they traveled. So you have to base that on which side's the cathode and the anode. Other questions about galvanic? Jay, does that answer your question about that you asked me earlier?
Yeah.
Okay. I'm gonna look in this book here. This one, they had some good AP tips. So on the top of 299, they have those mnemonic devices. Those are the ones I don't remember if I said Leo Gosger today. I know I said that last night, but gaining electrons is reduction, and Leo is losing electrons is oxidation. So that's a good way to remember which one's which. We said it was spontaneous. Yeah. On page 305, I really liked this chart. Talked about it yesterday. This is a really great chart on 305. It talks about the difference between galvanic and electrolytic. The signs of the cathode, the sign of the anodes are different on the two, because this one you're looking at which way the electrons are naturally moving. So your anode is losing its electrons, whereas on the electrolytic one, you're forcing electrons one way, and so it causes a buildup of electrons, and so it kind of happens a little bit differently. So that causes your charges on those to become different. But your cells, we also talked about already, are also going to have different signs. Galvanic's got to have an overall positive cell potential because we're making energy, and electrolytic will have an overall negative cell potential. And then we talked about the ion transfer already. So. So here, remember how we talked about on our cathode one that we're like gaining these electrons, right? And so when these electrons are coming over here, it's causing your positive ions to be kind of attracted to it. And so when you have these extra negatives that are picked up on the side, it's talking about the, like, yes, it's talking about the metal. That's the best way to say that.
Because the solution of the anode
is right. The solution over here is going to decrease in being positive. So that's why we have to pull the positives in. I don't know. What else do you guys want to ask about? Any other questions? Do you have any questions not about electrochemistry? Sure. Takes kind of a while to do an electrolytic cell, but I will try to do a quick one. I need some, I don't have cell potentials memorized, so I need to have some of those. It's really really struggling on the video last night with copying them out of the book. And try to do a better job.
It's just like this.
I don't know why, I'm just really can't copy the things out. Okay, electrolytics tend to happen in one container. And within your container, you're going to have still your 2 electrodes and what we would call a power supply. And so this power supply provides the energy that's needed. Your electrodes tend to be inert substances. The example they gave in the book wasn't an inert substance, and I don't see that happen very often, so I'm going to go ahead and stick with the inert substance. And I'll talk at the end about how it's a little bit different when it's not. But so when I say inert, like it could be platinum is a good example. That's a metal that doesn't tend to react with very many things. And they can also be containers that just hold different gases, and that can work as well. And then inside here, it's a solution. So we, of course, have water. And then you're going to have some sort of salt. Any salt would go in here. And from there, you're going to make some choices. Because these are the electrode values, or cell potential values, I mean, these are the ones I'm going to use. I'm going to use a solution of copper sulfate to put in here. And within my copper sulfate, I have to make some choices. This is an electrolytic cell, so it's non-spontaneous. I have to turn on my power supply, so I'm going to be losing my volts overall. And when I turn on the power supply, that forces electrons one direction. Let's say my electrons are traveling this way. So notice I'm kind of figuring out what's happening in my cell backwards from the way I did with galvanic, because you sort of work from the power supply out, and then you kind of go from there. So if my electrons are transferring that way, then this side is losing my electrons. So that makes this side my anode. And this side is gaining the electrons, so that makes this side my cathode. So far, so good. And then since this, what do I want to say? This side is gaining the extra electrons. It's going to have a buildup of a negative charge. And since it's got a buildup of a negative charge, it's going to pull anything towards it that has the potential to be like it's going to be attracted to those negatives. So like my copper is going to go that way. My water's already floating around there. And so we're going to look at what might happen to allow it to perform reduction. So we're going to look at these values based on our reduction potentials. So copper is a positively charged substance, so that looks like a great possibility. So this copper is going to be attracted to that. We said water's already floating around in there, so water is going to be involved. But if you notice on my chart, I have 2 reactions that involve water. We have this one and we have this one. So you have to make a choice as to which one is most likely to occur at the cathode. The one that's going to occur at the cathode has to be the one that's getting reduced. So you can tell which one's being reduced because the water and the electrons are on the same side of the equation. When they're on the same side, that's showing that they're coming together. They're being added together. So it's gaining electrons. So that's why I'm going to use that water. as a possibility. Remember, we're just looking at options here. Negative 0.83, 0.20. So I'm going to come back to that one in just a minute before we make any choices. And we're going to look at our anode side and kind of do the same thing. So in our anode side, our electrons are leaving, so it's going to have a positive charge. So it's a buildup of positives on that side. And when that happens, then my negatives tend to be attracted to that side. So sulfate would make sense to be on this side. Problem with sulfate is that if you were to look at our equation here, this is the only thing they've provided for us. And notice sulfate and electrons are on the same side of the equation. So it actually doesn't have the ability to be oxidized. So it can't be sulfate because it can't be oxidized based on the information that they've given me here. So my next option would be the water. And once again, I have to make a choice between my two waters. And my water here is on the opposite side from my electrons, so it can show how they're separating from each other. Even though it's written in this direction, if I flip this equation around and I have it so that water is a reactant, then you can see how now the electrons are being pulled apart from my water molecule. And so since I flipped it around, it makes it become negative 1.23. Here's where I'm going to take a moment to talk about another possible situation. Copper here would have the potential to be oxidized if and only if my electrode were made out of solid copper. And so if I had a copper electrode, then I could also put copper in here as a potential oxidation reaction. And if that were what's happening, copper would have been the one that gets oxidized. But I don't see that happen very often. They usually see electrolytics with inert substances, and they usually save that metals for the galvanic. So I am not going to show that, but that is the example they did in the book. So if you want to look at that, you could see how that works. But so that leaves me with the only option here to have oxidation would be for that water molecule. And so then I'm going to come back to this side. Sulfate we established could be reduced. So I'm going to go ahead and put him in this group here as a possible option. 4+ is probably not what that's supposed to say. Is it supposed to say H+? I'm going to assume. So once again, I have these values. Now they're not in any sort of order. My sulfate is 0.2, my water is negative 0.83, and my copper is 0.34. So just like, again, I'm looking for which one's most likely to be reduced, I'm looking for the most positive value. And so in this situation, copper comes out to be the most positive. So that tells me on my cathode equation is going to be my copper, 2 ions, and in this setup, my anode equation is that water equation. So then if I wanted to find the sum of those two, I had 4 electrons that were being lost here, so I'm going to go ahead and double my coppers. But remember, still not changing anything about my value. It had 0.34. I'm not going to rewrite that whole equation, but it was negative 1.23. Don't want to calculate that. What do we get? You guys do it. I have faith that you guys can do it in your head. I don't have any way to calculate it. What'd you get? Thank you. Okay, I have a negative value. Is that okay? So it's not spontaneous. That's what we want to get. Yay, success. More questions on electrolytic?
Is this where the freeze
this would be the same kind of situation. This particular cell would just be like regular electrolysis, but you would use an electrolytic cell to electroplate something. And the only differences are what you use for your solution and what you would use for your substances on the inside here. Because if you wanted to electroplate something, you would use, let's say, a solution of Ag plus and NO3 minus. And so you'd have an Ag metal and then whatever you wanted to electroplate on one side. That's a spoon. Does that look like a spoon? Maybe I should make it a fork. Anyway, whatever. You guys know. It's a spoon. Go with it. And so if you wanted to electroplate that, then you could have it so that it causes it to gain those electrons. So you need to force one side to be turned into a solid. So you want to make your ions gain their electrons to become their solid. So I guess I should draw them the opposite sides. Because you want your cathode to be gaining the electrons to turn it into a solid, so it picks it up this way. So I need this side has to be my cathode. But it all needs to be the silver. And then when we do our calculating, you have to do some stoichiometry with it. So you just want to be really careful with your values. And remember things like an amp is the same thing as how many coulombs per second. And Faraday's constant is 96,485 coulombs per 1 mole of electrons. That's Faraday's constant. They give you those values, so you just have to be comfortable with using them. That's what's important. And we did work through an example yesterday over those, but I'm happy to do one now if you want.
So what kind of questions will be asked that involve like the stoichiometry? Will ask about like seconds?
Yeah, it could ask any number of questions. It could ask a question that says, you give a 10 amp power supply and you want to electroplate 5 grams of your substance. How long is it going to take to do that? Or in the reverse, you've got 10 amps and it takes 30 minutes. How much can you electroplate in that time? And then the example we did yesterday was you had 10 amps and you had 5-point-something grams of silver, or not silver, of some unknown metal. And your job was to figure out what the type of metal is in your substance. And so essentially you had to solve for molar mass. So they gave you grams and you were solving for moles. And then you take grams divided by moles. And that was the problem we worked out yesterday. Can do whatever you guys want me to do now. If you want me to do it again. How many seconds does it take? Sure. So if we were going to be looking for seconds, we'll just use the nickel equation because that's the one that's here on top. And let's say we have 20 amps of our substance, and we have, 6.25 grams of our nickel that we want to electroplate. Okay, and our question is, how many seconds? This is probably going to be a lot of seconds. Made up numbers. So I have 2 choices. I only have 2 numbers to choose from, which one I want to start with. We don't start with amps because amps is a conversion, a way to switch between coulombs and seconds. And so I'm going to start with my 6.25 grams of nickel. If you started the other way, just follow your units. It will still work out. This one is just one you're more used to. So then grams of nickel needs to go on the bottom, and the best thing you're pretty much always going to change grams into is going to be to moles. I cannot remember the mass of nickel off the top of my head. 58. So 58.7 grams of nickel to 1 mole of nickel. And then when I'm dealing with this reaction, I need to use my balanced equation. And so for every 1 mole of nickel, I'm going to need to make 2 moles of electrons. So 1 mole of nickel, 2 moles of electrons. And now that I've got moles of electrons on top, I can use Faraday's constant. And for every 1 mole of electrons, I can transfer 96,485 coulombs. Running out of space a little bit, so I'm going to get rid of this information. And then I've got coulombs on the bottom, and I need to turn it into something that works, which is seconds. It's really convenient because I figured out earlier that I had 20 amps. So if 20 amps is how many coulombs per second, that tells me I have 20 coulombs per 1 second. So now I've canceled out any units that aren't seconds. So I'd multiply and divide. Like I said, it's going to be a fairly large number. I still don't have a calculator. So if you guys want to know an answer, you'll have to calculate it out.
On the test, would they expect us to know the 96,485 or would you just the 96?
I believe they give you both of those numbers. They wouldn't expect you, I think, to memorize anything. I put 96,485 because I was thinking that's what it was on the sheet, but I could be. One year it was one number and then they switched to the other one, so I might have them flipped. Whatever's on your sheet, go with it. Yep, they have 96,485. Okay, guys. Thank you. Appreciate it.